Hello and welcome to Lecture 5 of our course on Stochastic Modelling of Biological Processes. Today, we will continue in our presentation of Chapter 2, discussing differences between deterministic and stochastic modeling of chemical reaction systems. Many of our examples in previous lectures were chemical systems with only one chemical species. For example, in Lecture 1, we discussed the production-degradation system 1.9. It is a chemical system with one chemical species called A, which is degraded with rate constant K1 and produced with rate constant K2. Its classic deterministic description is given by this ODE for concentration, which we denote by a lowercase letter a. This ODE has one stable steady state given as K2 over K1, and all solutions through this ODE converge to the stable steady state as time t goes to infinity. We also observe that the results obtained by the Gillespie algorithm looked like noisy solutions of the ODE model. In fact, the classic deterministic ODE description provided the exact description of the average behavior of the stochastic model. In Lecture 4, we discussed the chemical system 2.1 with the following four chemical reactions. The corresponding deterministic description was given as this ODE with a cubic polynomial on the right-hand side. Depending on the values of parameters K1, K2, K3, and K4, this ODE can have one or two stable steady states. The solution of the stochastic model again fluctuated around a favorable state of the system, but we could also observe stochastic switching between the favorable states for some parameter values, provided that the system dynamics was computed for a sufficiently long time. In summary, considering models with one chemical species A, their deterministic description is a single ordinary differential equation for its concentration, which we denote by a lowercase letter a. It is an ODE with a polynomial right-hand side. Putting the right-hand side equal to 0, we can identify all stable steady states and observe stochastic switching between the favorable states of the system for some parameter values. Convergence to a steady state is arguably the simplest possible long-time behavior of the deterministic model of a biological system. For some other systems, we can also observe oscillating solutions. For example, circadian rhythms have a period that lasts approximately 24 hours. Circadian rhythms are internal processes that regulate the sleep-wake cycle in animals and plants. They are driven by a circadian clock, which is a biochemical oscillator. Another example of a model with oscillations include predator-prey equations, describing the dynamics of biological systems in which two species interact, one as a predator and the other as prey. In this lecture, we will discuss deterministic and stochastic modeling for chemical systems with oscillations. I have put the phrase with oscillations in quotes because in some cases there will be no sustained oscillations in either the deterministic or the stochastic model. We have three possible cases. First, both deterministic and stochastic models could oscillate. Second, the stochastic model could oscillate, but the deterministic model will not. And finally, the deterministic model can sometimes have oscillating solutions, but there will be no sustained oscillations in the stochastic model. We will see examples of all three cases. Since a single ordinary differential equation cannot have oscillating solutions, we need at least two chemical species to get oscillations. In this lecture, all our illustrative examples will be written in terms of two chemical species A and B. Then, their deterministic description will be given by plain autonomous systems of ODEs for their concentrations, which have polynomials on the right-hand side. Our first example is described in detail in section 2.2. It is a system of two chemical species, A and B, in a reactor of volume nu, which are subject to the following four chemical reactions. Both chemical species are produced with constant rates, denoted K2 for the production of A and K4 for the production of chemical B. Chemical A is also degraded with rate constant K3. Finally, we have this trimolecular reaction, where two molecules of A and one molecule of B react to produce three molecules of A. In other words, the reacting molecule of B is effectively converted into another molecule of A. In some mathematical biology literature, this system is named after Schnackenberg, who introduced it as a simple system with a limit cycle. Our treatment of this system follows later work, where it has been used to study differences between deterministic and stochastic modeling. The classic deterministic model is given as the following system of ODEs for concentrations, which we denote by lowercase letters. It is a plain autonomous system of ODEs with polynomials on the right-hand side. The first reaction produces A and removes B, so it corresponds to this positive term on the right-hand side of the first equation and this negative term on the right-hand side of the second equation. The production and degradation of A is reflected in these two terms, K2 minus K3A. And the production of B corresponds to this constant term K4. Since we want to compare the deterministic model with the results obtained by the Gillespie algorithm, we rewrite the ODs for concentrations in terms of ODs for the approximate numbers of molecules of A and B, which we can obtain by multiplying the concentrations by the system volume nu. Therefore, we multiply ODs 210 and 211 by the system volume nu to get the following ODEs. They include four parameters. The first one is K1 divided by volume squared, and the others are K2 nu, K3, and K4 nu. These are exactly the same four parameters which we need to specify to apply the Gillespie algorithm. In the following plots, we will use the same parameter values for both the deterministic and stochastic models. Our first comparison is shown in figure 2.3 on page 39. In the left panel, we can see the time evolution of the number of molecules of A. I use the same initial condition for both deterministic and stochastic models, starting with 10 molecules of A and 10 molecules of B in the system at time 0. And I computed the time evolution of the system for 80 minutes, using the parameter values given in the lecture notes in equation 2.14. The red line is the solution of deterministic ODEs. As you can see, it converges to a steady state value which is around 10. On the other hand, the stochastic model, the blue line, shows relatively regular oscillations. At approximately equidistant time intervals, the blue line can reach the values of thousands of molecules in the system. Here I would like to note that we use the log scale on the vertical axis to highlight that the blue line includes some stochastic fluctuations for smaller values. It fluctuates around the deterministic solutions, but then it dramatically increases. In the right panel, I plotted the results of the Gillespie algorithm again, but this time using a normal scale on the vertical axis. The solid line shows the time evolution of the number of molecules of A. Using the normal scale on the vertical axis, we do not see any fluctuations for smaller values. In the right panel, I also added the time evolution of the number of molecules of B. The number of molecules of B slowly grows from low values to large values and then quickly drops down. We can observe relatively regular oscillations in the stochastic model, so this model could be considered as an example of a chemical system for which the stochastic model oscillates, but the deterministic model does not, at least for the considered parameter values. Next, let us change the parameter values. I will only change one of them, the production rate K for new, which in the above simulation was equal to 25 per second. In figure 2.4 on page 39, we change this value to 100 per second. The time evolution of the number of molecules of A is plotted on the left, and the time evolution of the number of molecules of B is plotted on the right. We observe that both stochastic and deterministic models oscillate for this new set of parameter values. Oscillations of the deterministic ODE-based model are regular, but we observe that stochastic oscillations look also relatively regular. Again, we have used the log scale on the vertical axis of the left plot. We would not see any of these fluctuations if we use the normal scale. Running both models for different sets of parameter values is one possible way to compare the deterministic and stochastic models. But we will get more insights into explaining the model behavior if we apply the techniques of phase-plane analysis, which students taking this course in Oxford have covered in their introductory course on differential equations. Therefore, in figure 2.5, we replot our results in the phase plane, putting the number of molecules of A on the horizontal axis and the number of molecules of B on the vertical axis. Null-clines of the deterministic ODEs are plotted as green lines. The null-clines intersect at the steady state, which is highlighted here as this red circle. We can use the steady state analysis to conclude that this steady state is stable for our parameter values 2, 14, which are used in the left panel. Changing the parameter value k for new, we are moving this null-cline. But the other null-cline does not change, so we are effectively moving the steady state along the other null-cline as the parameter k for new increases. Going from the left panel to the right panel, the steady state not only moves, but it also becomes unstable and the ODE system has oscillatory solutions. It has a limit cycle, which you can see here. Changing our parameter values k for new from 25 to 100, the ODE system undergoes a bifurcation. In general, a bifurcation occurs when a small smooth change made to a parameter value causes a sudden qualitative change of the behavior of the system. In our case, it changes from the convergence to a steady state to oscillatory solutions. To understand the behavior of the stochastic model, I again use the log scale on the horizontal axis corresponding to the number of molecules of A. Looking at the left panel, we can see that the stochastic trajectory is initially following the deterministic trajectory with some fluctuations. But then the fluctuations become large enough so that they can help the system to jump to another part of the phase plane. In this part of the phase plane, the deterministic trajectories would look relatively similar to the stochastic ones again, but they would all end up in the stable steady state. In particular, during most of these cycles, the stochastic and deterministic solutions are relatively similar. It is only in this region where noise helps to avoid the stable steady state and leads to sustained oscillations. The key point in our first example was that the system was close to a bifurcation point of its deterministic ODE model. A similar behavior can be expected from other systems. To illustrate this, I will discuss here another system of two chemical species, which is taken from one of our papers. It is a system of 7 chemical reactions. Its approximate deterministic description is given by the following system of ordinary differential equations written for concentrations of chemical species A and B. The first chemical reaction is the production of chemical species B with rate constant K1, so it corresponds to constant term K1 in the second differential equation. The next chemical reaction is the conversion of chemical species B to chemical species A. So this term appears in both differential equation with positive sign in the first one, K2B here, and with negative sign K2b in the second differential equation. Next chemical reaction is the degradation of chemical species A with rate constant K3, so it corresponds to term minus K3A in the first differential equation. The next two chemical reactions are written as this reversible chemical reaction where 2A can go to 3A and back. These two reactions correspond to two terms on the right hand side of the first differential equation, minus K5A cubed plus K4A squared. Finally, the last two reactions do not change the number of molecules of A. They correspond to two terms on the right hand side of the second differential equation, minus K7A squared B plus K6AB. Since we want to compare the results of these ODEs with the corresponding stochastic model, we again multiply the deterministic ODE system by the system volume nu to obtain ordinary differential equations for the approximate numbers of molecules of A and B. They are given as these ODEs. They include the same 7 parameters which we need to specify when we apply the Gillespie algorithm. In our illustrative results, I will use a set of parameters which appeared in this paper. In particular, I will fix the values of 6 rate constants K2, K3, K4, K5, K6 and K7, and I will also consider the fixed system volume nu. Therefore, 6 of the parameters which appear in these ODEs will be fixed to specific values. I will vary the first parameter, the production rate K1 of chemical species B, which I have highlighted here in red. Therefore, our bifurcation parameter which we will vary is K1 nu. To get some insights into the dynamics of this model, I have plotted here the corresponding phase planes for two values of my bifurcation parameter K1 nu. I plotted the A null line as the red line. Since my bifurcation parameter does not appear in the first differential equation, the A null line is independent of K1 nu. In particular, the red line is the same in both panels. On the other hand, the B null line changes, so this green curve is different in each plot. In the left panel, the B null line has 3 intersections with the A null line. So there are 3 steady states of the system. These 3 steady states are saddle, stable node and unstable node. Going from the left panel to the right panel, I am increasing the value of my bifurcation parameter K1 nu from 480 to 520. By doing this, I am moving the green null line and these two steady states will move closer to each other. If K1 nu is equal to approximately 488, then the saddle and the stable node become one point. The null lines will be touching, so this will be the bifurcation point. If I increase the value of my parameter K1 nu above 488, then there is no stable steady state anymore, and the system has oscillatory solutions, as you can see in the right panel for K1 nu equal to 520, where the plotted illustrative trajectories oscillate. In general, if we start a trajectory close to a saddle, then it takes a very long time to leave the saddle. Therefore, at the bifurcation point, the limit cycle will have an infinite period, which explains one of the names for this bifurcation. It is named as a sniper bifurcation, which stands for the saddle, node, and infinite period cycles. Or SNIC bifurcation, which stands for the saddle, node, invariant circle bifurcation. In this bifurcation, a stable node and saddle point simultaneously occur on a limit cycle. So if we start with the right panel, where we have sustained oscillations, and we decrease the parameter value k1 nu towards the bifurcation point 488, then speed of the oscillation slows down and the period will approach infinity. You could now pause this video and try to guess yourself what type of behavior you could expect from the stochastic model. What will happen when we simulate the dynamics of the system using the Gillespie algorithm for the same parameter values? What will happen in the panel on the left? What will happen in the panel on the right? Now I will give you 5 seconds to think about these questions. But if you need more time, you can press the pause button. Well, as our first guess, we could expect that the behavior of the stochastic model could follow the behavior of the deterministic trajectories with some noise. In particular, for the right panel, we could expect oscillations and both deterministic and stochastic models could oscillate. On the other hand, for the left panel, we could expect fluctuations around the favorable state of the system, which could be close to the stable steady state of ODEs. However, we have already seen in our previous example that noise can help us to escape from favorable states of the system. If the noise is sufficiently large, then the stochastic trajectory could jump beyond this saddle. So we could observe some stochastic oscillations. And this is indeed the case, as I'm illustrating here with the results computed by the Gillespie algorithm. We observe that for both parameter values, the stochastic model seems to oscillate. In the left panel, the stochastic trajectory, visualized as the blue line, initially approaches the favorable state of the system with some fluctuations. But then the noise can sometimes become large enough for the trajectory to jump to another part of the phase plane. In this part of the phase plane, the deterministic trajectories look relatively similar to the stochastic ones again. In particular, during most of these cycles, the stochastic and deterministic solutions are relatively similar. It is only this region where noise helps the trajectory to escape the stable steady state, which then leads to sustained oscillations. In the right panel, you can see the system behavior for the parameter value k1 nu equal to 520, where both stochastic and deterministic systems oscillate. We can also visualize the same trajectories as functions of time. Here I plot the time evolution of the number of molecules of A. This visualization again confirms that the deterministic model converges to the steady state for lower values of our parameter k1 nu, and the deterministic model has oscillatory solutions for larger values of k1 nu. The stochastic model oscillates for both parameter values. These stochastic oscillations are not as regular as before, but we can estimate some statistics from the results obtained by the Gillespie algorithm. For example, we can estimate the average period of oscillations. I have done this for several values of our bifurcation parameter k1 nu. For each value, I have run the Gillespie algorithm and estimated the average period of stochastic oscillations. The results are plotted here as blue points. I have also added the period of oscillations of the deterministic OD-based model as this red line. We have already discussed that the period of oscillation is infinity at the bifurcation point 488, and the deterministic model does not oscillate for smaller values of k1 nu. On the other hand, the stochastic model oscillates for all considered parameter values. In this plot, blue points were obtained as averages over 10,000 periods computed by the Gillespie stochastic simulation algorithm, which can be computationally intensive. So the obvious next questions are, can we obtain the same information by analyzing suitable equations? Or in general, how can we systematically investigate the dependence of the behavior of stochastic chemical systems on their parameters? We will return to these questions after we present some additional theory in Chapter 3. Considering our first illustrative chemical system 2.9, its further analysis is included in the lecture notes in section 3.9. This brings me to the end of lecture 5. Considering deterministic and stochastic modeling for chemical systems with oscillations, there are 3 possible cases. First, both deterministic and stochastic models can have oscillatory solutions. Second, the stochastic model oscillates, but the deterministic model does not oscillate, and vice versa. The cases 1 and 2 were illustrated in our examples in detail. We have discussed 2 simple systems of chemical reactions for parameter values, which were close to the bifurcation points of their deterministic OD-based models. We observed that their deterministic description can converge to a steady state, while the stochastic model of the same system of chemical reactions can have oscillatory solutions in some parameter regimes. The case 3 can be illustrated on many systems. For example, one can use classic Lotka-Volterra predator-prey system, which provides a basic example of an oscillating system in introductory courses on differential equations. We write it as a chemical system for 2 chemical species A and B, where A represents prey and B represents predators. They are subject to the following 3 chemical reactions. The first one is A goes to 2A, which models that prey reproduce exponentially. The second reaction represents the loss rate of the predators due to either natural death or immigration. It leads to an exponential decay in the absence of prey. The rate of predation upon the prey is assumed to be proportional to the rate at which the predators and the prey meet. And, using our chemical reaction formalism, predation is described by the third reaction. So this would be an ecological predator-prey motivation behind this chemical system. But you could also assume that A and B are 2 molecular species which are subject to 3 chemical reactions. If we use these chemical reactions and write a corresponding deterministic OD-based model, it has oscillatory solutions which are always positive. On the other hand, for any initial condition, there is always a non-zero probability that the random number generator used in the Gillespie stochastic simulation algorithm selects reactions in such an order that we end up with either no molecules of A or no molecules of B in the system. In particular, there are 2 types of long-time behavior of the stochastic model of the Lotka-Volterra system. First, extinction of A, prey, is followed by extinction of B, predators. If there are no prey A in the system, then the third reaction cannot occur, and all predators are removed from the system because of the second reaction. The second possibility is that predators are extinct first, then there will be no predation and prey will reproduce exponentially. In particular, the Lotka-Volterra system is an example of case 3, where the deterministic system oscillates, but the stochastic model does not have sustained oscillations. This brings me to the end of our discussion of section 2.2. Please read pages 37 to 42 of the lecture notes before watching the video of lecture 6. Thank you very much for listening to lecture 5 of our course on stochastic modeling of biological processes. Bye bye.